Hi, I'm John, and I'm going to talk about joint work with Brooks, Matt, Marvin, and Miguel, where we show how to explore and search over molecule space effectively by generating molecule synthesis directed acyclic graphs or DAGs. For molecule search, we want to answer not only what molecule to make, but also crucially, how to make it. But first, why is molecule search important? Well, molecule design is particularly important in the search for new drugs. This is currently a very expensive process. Now, a significant chunk of this cost comes down to the high number of select-make test cycles required. In each iteration, a chemist selects a molecule to check next, makes it, and then tests how well it performs. There's been a series of recent work looking at how machine learning can help within this cycle, particularly at the select step. In a traditional approach, such as virtual screening, the molecules that are being selected come from a pre-built database of purchasable or otherwise available compounds. To remove the limitation of only searching in a predefined set, machine learning approaches have built generative models of molecules. These models can suggest new molecules through generating text representations of them or by directly outputting molecular graphs. However, the size of the chemical space is not the only axis in which we are interested in when reasoning with and exploring molecules. We are also interested in how stable the molecules suggested are and whether they are synthesizable, i.e. whether they can actually be made in practice. As after we have selected a molecule, the next step in our cycle is to make it. This is a crucial consideration which is ignored by many recent machine learning approaches. So what we seek to address in this work is there a middle ground here? Can we explore more of chemical space whilst maintaining the synthesizability of the molecules we suggest? So to do this, instead of generating a molecule directly, in this work we generate a molecule synthesis DAG, such as the one shown on this slide for paracetamol. This DAG describes how easy to obtain and purchasable building block molecules, shown here in blue, react together to form more complex product molecules, shown here in these green boxes. We believe that modeling molecules in this manner not only informs you how they are made, but also provides an inductive bias for stability. In the remainder of this presentation, I want to talk about how we do this in more detail. In particular, I want to focus on three particular aspects of our work. Firstly, how we serialize and model such a DAG. Then secondly, some variants of this basic model we propose to use in existing machine learning frameworks. Before thirdly and finally, I want to quickly go through some empirical results. So firstly, how do we set up our model to generate a synthesis DAG? Well, as you can see, a synthesis DAG is made up of a number of different nodes and edges, which I've broken up here and which we need to construct one by one. Each node in the DAG is associated with a molecular graph, and the edges represent reaction relationships between these molecules. We can then call the entire structure a DAG of graphs. We serialize the DAG so that we can describe its construction, which happens in a bottom-up manner, through a series of actions. The main type of action we take is to add a new node to the graph. These can be building block nodes or product nodes. Then conditioned on this kind of node we have two other types of actions, which decide on the node's molecular identity. For building block nodes, we choose between molecules in a pool of readily available compounds, whereas for product nodes, their molecular identity is instead informed through their reactants, which corresponds to adding edges in our graph. So having selected a product node, we carry on selecting edges into it until we choose to create either an intermediate or final product, in which case our construction sequence ceases. By serializing the construction of the DAG, we can then model the probability of taking an action at any point using an autoregressive model, taking into account all of the previous actions chosen. In practice, we do this using a recurrent neural network, which I've drawn on this slide, unrolled over a few time steps. This recurrent neural network takes in the previous actions chosen and updates its hidden layer to act as a context vector describing the current state of the DAG. When representing molecules into this network, we use embeddings produced by graph neural networks. We consider two variants of our model, one which we call DOGGEN for DAG of Graphs Generator, which is the generative model just described. After training our model, we can sample new molecules from it autoregressively by sampling the actions one by one. Alternatively, we can also use this model for optimization, and we demonstrate this in our paper using a simple algorithm based on the cross-entropy method. This works by sampling new DAGs from the model, assessing the DAG sampled on a particular optimization task, and then fine-tuning the weights of our model on the best performing samples. As we do this again and again, the distribution of the properties of the molecules we generate gradually improves. The second model variant we developed is called DOGAE for DAG of Graphs autoencoder, where we use our DAG generator as the decoder in an autoencoder structure. For this model, we also develop an encoder, which given a DAG of graphs, parameterizes a distribution over latent space. This encoder is based around a hierarchical graph neural network that performs two stages of message passing. The first stage of message passing occurs on the molecular graph associated with each node of the DAG. Here, messages are passed between the atoms within a molecule before being summed to create molecule-level embeddings. The second stage of message passing occurs over the synthesis DAG structure itself, where these initial molecule embeddings are then updated by passing messages forward on the DAG between the molecules. As well as using DOGAE for sampling new synthesis DAGs, we can also use such a model to perform interpolation in molecule space. To demonstrate this, on the next few slides, I'm going to show the different DAGs we decode to when performing a random walk in the latent space around a DAG in our training dataset. So this process is summarized by the cartoon on this slide. We will move randomly about locally in the latent space and decode out to different DAGs. So to begin, on this slide, I've drawn out our training dataset DAG, as well as some other building block and product nodes that exist in our dataset. Initially, our model correctly reconstructs this DAG. Now here, after walking randomly in the latent space, I plotted the first new DAG we decode to. One can see that it shares similarities in substructures with the original DAG, which is to be expected as they're close in latent space. However, also I should point out that it's suggesting new reactions which we haven't seen before, which I'm indicating here using these dotted lines. If we perform the random walk for longer, we continue to explore new DAGs around the original one, using different building blocks and new reactions. So here, due to the structure of our decoder, the continuous latent space we have learnt allows us to interpolate in this reaction network space, discovering new nodes and new molecules, as well as potential synthetic routes between them. In terms of quantitative benchmarks, we mainly assess our model in two settings: sampling and optimization. Firstly, when assessing our model on sampling benchmarks, we see that we can match the chemical space coverage of several previous generative approaches. This is despite our model being constrained to generate synthetic molecules, whereas many of these previous approaches do not have this constraint. Secondly, we look at the performance of our model on a series of property optimization tasks, where we always find a molecule that is better than those in the training set, shown here by being above these dotted grey lines. We also compare our performance against unconstrained models. Going into this, we generally expect that these models should outperform ours, considering just raw property scores, given that they lack the same constraints. So it's again encouraging that we obtain competitive results. Even more encouraging, though, is the fact that when we then compare the top molecules found by each approach, many of these unconstrained approaches produce far more unstable or unsynthesizable molecules than our model. So to briefly summarize what I've talked about, I introduced our models DOGAE and DOGGEN, which generate molecular synthesis DAGs. I showed how these models are able to obtain competitive results in optimization and sampling tasks when considering just raw property task score, but also generate stable and synthesizable molecules too. This has often been neglected by many previous machine learning approaches, although I wanted to briefly add that I think this is quite an exciting time for this area and is beginning to change. So if you're interested in this too, I encourage you to check out these other recent relevant works. Ultimately, we think that explicitly modelling synthesizability is important to better reflect the real search task, and so we hope that the method we propose is a step towards reducing the time needed in the select-make-test cycle when searching for new drugs.